Hello students, welcome to the new video. The first question is, find the response of a system with transfer function h of s equal to 1 by s plus 1 into s plus 5 for a unit step input. Okay. So in the question we are given h of s, the transfer function, as 1 by s plus 1 into s plus 5. Okay, and in the question, input signal given is u of t equal to, x of t equal to u of t. Okay, so input is x of t equal to u of t. So what should be x of s? Laplace transform of u of t is equal to 1 by s. Okay, so what we know is the transfer function is h of s and the input transform is 1 by s. So according to the convolution theorem, we know y of s, the transform of the output signal y of s, will be equal to x of s into h of s, which can be written as 1 by s into 1 by s plus 1 into s plus 5. Okay, so the only thing or the only major plan left behind us is to make this a partial fraction. So let me make it as a by s plus b by s plus 1 plus c by s plus 5, because all these are a power of factors of power 1. So now what we have to do is to find the values of a, b and c. So let me illustrate you a very simple method. The value of a will be equal to, what is the denominator of a? It is s. Okay, you multiply s with this transfer function, the whole transfer function. What happens? S and s cancel. Okay, remaining is 1 by s plus 1 into s plus 5. Now put s as some value which makes a by s infinite. Okay, put some value for s in the remaining s plus 1 and s plus 5, so that value makes a by s infinite. What is that value? It is nothing but s equal to 0. So put s equal to 0 in these two factors. Okay, so a equal to, I can first one I will illustrate elaborately. So s into, s into denominator of a is s into the whole of the transfer function, s into s plus 1 into s plus 5, evaluated at what? Evaluated at s equal to a number which makes this factor, this term alone, to infinite, that is s equal to 0. So evaluated at s equal to 0. This is very simple now. So that implies a equal to 1 by s is 0, right? 0 plus 1 into s plus 5 becomes 0 plus 5. So this is 1 by 5. So we got a as 1 by 5. Okay, in a similar fashion, let us find out the value of b. So b is equal to, the denominator b is s plus 1. So multiply s plus 1 with this whole transfer function. So you will get only 1 by s into s plus 5. S plus 1 gets cancelled. Okay. Now evaluated at what? Evaluated at s equal to a value which makes this term alone as infinite. What is that value? That is clearly, evidently, it is minus 1. So put s equal to minus 1 and evaluate this. So 1 by minus 1 into minus 1 plus 5, which is equal to minus 1 by 4. So b equal to minus 1 by 4, a was 1 by 5. Okay. Now one more constant is there, c. So c is s plus 5 into the whole of the transfer function is s into s plus 1 into s plus 5, evaluated at what? Evaluated at s equal to minus 5. S equal to minus 5 will make this term infinite. So this is 1 by minus 5 into minus 5 plus 1. Put s equal to minus 1 in that fraction. So this becomes 1 by 20. Is that right? Right. So we got a as 1 by 5, b as minus 1 by 4, and c as 1 by 20. Now things are very easy. Just put a, b and c in this equation. That will give you y of s is equal to 1 by s into s plus 1 into s plus 5 is equal to a by s. A is 1 by 5. So 1 by 5 by s plus b is minus 1 by 4. So minus 1 by 4 divided by s plus 1 plus, and finally c is 1 by 20. So 1 by 20 divided by s plus 5. Okay. So this is clearly, you can see all the terms are known Laplace transforms. So it's very simple to find out the inverse transforms. Therefore y of t is equal to 1 by 5 into, what is the inverse transform of 1 by s? It is e of t, minus 1 by 4 into, what is the inverse transform of 1 by s plus 1? It is e raised to minus t u of t, plus 1 by 20 into, what is the inverse transform of 1 by s plus 5? It is e raised to minus 5t, e raised to minus 5t u of t. We are assuming all these signals or the entire system is causal. Okay, so this could be the final answer. Okay, let's start the next question. You're given a causal LTI system and is described by the relation differential equation second order, and find the impulse response of the system. You have to find the impulse response h of t of the system applying Fourier transform. Okay, underlining applying Fourier transform. Okay, so let's start doing this. You are given the differential equation, so you can apply the differentiation, time differentiation property of Laplace transform of Fourier transform. What does it say? It says that d by dt of y of t is a signal, then its Laplace transform is s into y of s minus y of 0. Okay, if y of s is the Laplace transform of y of t, where y of 0 is the initial condition or initial value. Similarly, second derivative will have s square y of s minus s into y of 0 minus y dash of 0. Okay, where y dash of 0 is the value of d by dt of y of t at t equal to 0. But anyway, this is a transfer function problem. So because you're asked to find out h of t. Okay, its Laplace transform is h of s, that is transfer function. Transfer function is valid only if initial conditions are all 0. Okay, so d by dt of y of t is s into y of s, and d square by dt square y of t is s square into y of s. That's all we need to take out in this problem. So applying this, I can rewrite or apply a Laplace transform on both sides of the differential equation. Both sides of the differential equation. That will give me first term, it is d square y of t by dt square will be changed into s square y of s. Okay, plus second term is 6 into dy by dt. So Laplace transform of that term will give you 6 s into y of s, plus finally you have 8 y of t. So its transform can be simply given as 8 y of s, equal to right hand side you have 2 into x of t, its transform will be 2x of s. Okay, now you cannot barely or steadily proceed from this equation. That is not incorrect, it is perfectly correct, no problem. But listen to the question. The question says applying Fourier transform. Only because they are saying applying Fourier transform, let me convert this into its Fourier transform. How can you convert a system in Laplace domain into Fourier transform domain? It's very simple. Put s is equal to j omega, because you know we have already seen that Fourier transform is nothing but Laplace transform evaluated at the imaginary axis. At the imaginary axis means at s is equal to j omega. Okay, so applying that, we can write j omega the whole square into y of j omega plus 6 j omega into y of j omega plus 8 y of j omega gives 2 into x of j omega. Okay, again listen, what we have to find is h of t. but in order to get h of t, we have to find out h of j omega, not h of s here. In this particular problem, it is h of j omega. So find out h of j omega. It is nothing but h of j omega is actually given by y of j omega output transform by x of j omega input transform. Anyway, it is a transfer function or frequency response. So output by input will give you h of j omega. So I can consolidate all y of j omega terms as j omega square plus 6 j omega plus 8 is equal to 2 into x of j omega. Now I can easily find out y of j omega by x of j omega will give you 2 by j omega square plus 6 into j omega plus 8. Okay, you treat j omega together. That will be very simple. Okay, so 2 by j omega the whole square plus 6 j omega plus 8. Now can you treat j omega as a single variable, and can you visualize the denominator of this expression as a second order equation, a quadratic equation? Can you visualize it? Of course, it is very simple. It is like s square plus 6s plus 8, where s is equal to j omega, right? So I can find the roots of, or I can factorize this equation as 2 by j omega plus 4 into j omega plus 2. Okay, and this is now I can write y of j omega by x of j omega as h of j omega. That is the frequency response. You call h of j omega as frequency response, not transfer function, but frequency response. If at all h of j omega was in Laplace domain, I can call it the transfer function. That's the only difference between transfer function and the frequency response. Okay, so h of j omega equal to 2 by j omega plus 4 by into j omega plus 2. What should be the next step? It is nothing but obtaining a partial fraction. So again I can take as a by j omega plus 4 plus b by j omega plus 2. And how can you find the value of a? You cross multiply j omega plus 4 with this transfer function. It's not transfer function actually, with this fraction. So that will give you, and put j omega equal to minus 4, because j omega equal to minus 4 brings down this term into infinity. Okay, so I can write it down here. So it is 2 into j omega plus 4. I'm multiplying with j omega plus 4, and it will like this. Okay, evaluated at j omega equal to minus 4. That will give you 2 by minus 4 plus 2. Okay, and what is that? It is minus 1. Okay, so a is minus 1 equal to minus 1. Similarly, what is b? Can you calculate it in mind? B can be evaluated by multiplying the whole fraction with j omega plus 2, because it is in the denominator of b. Okay, so j omega plus 2 into 2 by, I'm writing the whole fraction as 2 by j omega plus 4 into j omega plus 2, and evaluated at what value? J omega equal to what value will make this term to infinity? It is j omega equal to minus 2. So j omega equal to minus 2, evaluated at j omega minus 2. So we can cancel this, and it is 2 by minus 2 plus 4, which is equal to 1. So I got b equal to 1. That gives b equal to 1 also. Okay, so a equal to minus 1 here and b equal to 1 here. So it is very simple now. So h of j omega equal to 2 by j omega plus 4 into j omega plus 2 will give a is what is a? Minus 1. So minus 1 into 1 by 4 plus j omega, and b is 1 plus 1 by 2 plus j omega. So that is the whole of my frequency response, h of j omega. And luckily h of j omega is obtained in two terms, all the two terms are known Fourier transforms, right? What is that? The Fourier transform of e raised to minus at is equal to 1 by a plus j omega, and we have these two terms, both of these terms in 1 by a plus j omega format. So we can write, therefore, h of t is the inverse Fourier transform of h of j omega, which is our impulse response that you have to find out in the question, is minus e raised to minus 4t u of t, right, plus second term is e raised to minus 2t u of t. So that is the final answer of this question. Okay, the next question is, obtain the transfer function of an ideal integrator in S domain. Okay, transfer function of an ideal integrator in S domain. So what is an integrator? An integrator is a system whose input-output relation will be y of t is equal to integral minus infinity to t x of tau d tau. If you are confused why I am using another variable, I can write it as x of t dt. Okay, but I have used t inside the limits also. So it is quite good if you substitute another variable inside this integral, because whatever be the integral, whatever be the variable, it does not affect the integral. Okay, so I can so it is fair if you, there's nothing wrong if you put x of t dt there, but it is good to denote it in another variable. So minus infinity to t x of tau d tau. Okay, now the question says to obtain the transfer function in S domain. So clearly do take Laplace transform on both sides. Take Laplace transform on both sides. So y of s is equal to, what is the Laplace transform of integral minus infinity to t x of tau d tau? Using the property of time integration, it is x of s by s. Okay, x of s by s. Okay, this is a very important relation. Now, what is the transfer function? Transfer function is nothing but h of s is the ratio of Laplace transform of the output signal to the Laplace transform of the input signal with no any initial conditions. So okay, so what is y of s by x of s from equation number 1? Y of s by x of s will give you the transfer function, and that will be 1 by s, right? That is clearly visible from this equation. Y of s by x of s will give you 1 by s. So this is the answer to this question, and it's a very important result for you to remember. The transfer function of an ideal integrator is 1 by s in S domain. Okay, let's find out what is in the next question. Find the inverse Laplace transform of the following function given by x of s equal to 3s square plus 8s plus 6 divided by s plus 2 into s square plus 2s plus 1 for ROC greater than minus 1. So ROC greater than minus 1 implies nothing but this is a causal signal, a right-sided signal, that much. Okay, now let us see what is x of s. So x of s has a numerator polynomial and a factor in denominator s plus 2 and a polynomial in denominator s square plus 2s plus 1. So first of all, what I have to tell you is, never get scared on such polynomials. In numerator, whatever be in the numerator, you don't actually have to take care of this. Whatever be this, don't mind. Okay, and in denominator, if you find a polynomial in denominator, find a way, if at all there is, find a way to factorize it. That is the easiest method to work out these problems. Just I'm writing here, just denominator, never care the numerator, only care the denominator. In denominator, if you find a polynomial, factorize it if possible. factorize it. Okay, that's the best, easiest method. So in this expression, x of s is equal to, what we have to find is the inverse Laplace transform. Okay, so making it partial fraction is the only, or is the simplest, easiest method to find the inverse Laplace transform. So for that, the first option is finding the factors in the polynomial if possible. So numerator I'm writing as such because that is not going to scare me anyway. And in denominator, s plus 2 is a factor itself, no problem, good. But the next term is a polynomial. S square plus 2s plus 1 is not a factor but a polynomial. But can you make it a factor? Of course you can, because it is nothing but s plus 1 the whole square. S square plus 2s plus 1 is s plus 1 the whole square. Okay, now we have got the denominators in factor form. It's very simple now. Now make it a partial fraction. Okay, whatever be in the numerator, never mind, you take it as a by s plus 1 the whole square plus b by s plus 1 plus c by s plus 2. Why did I take like this? Actually there are only two factors in the denominator, but we have taken three different constants because one of the factors is having a power 2, multiplicity 2. Okay, so if s plus 1 the whole square, then I have to write a by s plus 1 the whole square, then b by s plus 1, just 1. Okay, s plus 1 plus the other factor c by s plus 2. So this is the way, this is the way to write the partial fraction if you encounter any second order factors in the denominator polynomial. Okay, so now since this is this form, I mean factor square form, there is no any shortcuts to find out the constants a, b and c. The only way is to take the LCM, okay, and simplify. So taking the LCM, we will get, what we will get is 3s square plus 8s plus 6 is equal to a into, actually the LCM is s plus 1 the whole square into s plus 2. So under a in the denominator, s plus 1 the whole square is there, but s plus 2 is not there. So a into s plus 2 plus, similarly b has only one s plus 1, so we have to give one more s plus 1 and one s plus 2. Okay, plus c into s plus 1 the whole square. That is nothing, very simple. It's this is how we find the LCM. Okay, now what we do is expand. 3s square plus 8s plus 6 is equal to as plus 2a plus b into s square plus 3s plus 2. That's what we get if you expand these two factors, right? Plus c into s square plus 2s plus 1, that is s plus 1 the whole square. Now one more simplification, expanding the brackets. As plus 2a plus bs square plus 3bs plus 2b plus cs square plus 2cs plus c. This is what we get if you expand it. Okay, why did I do like this? Just to find out a, b and c by comparing the coefficient of particular powers of s. I will tell you how. Okay, first compare the coefficients of s square, okay, on both sides. So in LHS the coefficient of s square is nothing but 3, so I can write 3 is equal to, okay. In RHS, what is or are the coefficient of s square? We have this term with coefficient of s square and this term with s square. So b plus c is the coefficient of s square in the equation. Okay, so I can fairly write it as, so here b plus c is equal to 3. Okay, that will be equation number 1. Okay, now I can compare the coefficient of s the coefficient of s. In LHS it is 8, so I can write 8 is equal to, in RHS there are a lot number of coefficients with f for s, so I can write a, this is a, then plus 3b, then for s we have 2c, okay, plus 2c. So a plus 3b plus 2c equal to 8. I can write it as a plus 3b plus 2c equal to 8. My equation number 2. Okay. Now one more equation is to be obtained because we have 3 variables, so 3 equations are needed. So I can compare the constants, coefficient of s raised to 0, or I can call it constants, comparing the constants. In the LHS side we have a single constant 6, so 6 is equal to, and what are the constants on the RHS? 2a is a constant, it does not have any s, plus 2b is another constant, then plus c. Okay, 2a plus 2b plus c is equal to 6. So 2a plus 2b plus c equal to 6. That is equation number 3. Okay, now I can simply find a, b and c using any method. I can use determinant method, or 0 1, okay, sorry, I can write 1 3 2 8 for equation number 2, then 2 2 1 6, okay, 2 2 1 6 for equation 3, and 0 1 1 3 for equation number 1. Right, so this is the augmented matrix. I can do row operations or column operations, whatever. So 1 3 2 8. Now I'm doing R2 minus 2 R1. R2 gives R2 minus 2 R1. That means 2 minus 2 is 0. 2 minus 4 is 2 minus 6 is minus 4. 1 minus 4 is minus 3, and 6 minus 16 is minus 10. Right, and I'm writing the next row as such. Okay, now again I can convert this as 1 3 2 8. First row is as such, and I can write 0 plus 4 plus 3 plus 10. There is no change while we are multiplying the whole row with minus 1. And then okay, fine, 0 4 3 and 10. Okay, now what I'm doing is I'm going to change R3 as 4R3 minus R2. Okay, so first element is 0, then 4R3 means 4 minus 4 is 0, then 4 minus 3, 4 minus 3 is 1, then 12 minus 10 is 2. So this is what row operations will render you on that matrix. Now it is very simple. Take this row, the last row, you will get, this is for A, this is for B, this is for C. Okay, so C equal to 2. Directly we got C equal to 2. Fine. And the second equation will give you 4B plus 3C equal to 10. So 4B plus 3C, but C equal to 2, right? So 3 into 2 equal to 10. That means 4B plus 6 equal to 10. So B equal to 1. B equal to 1. Okay. Then finally this equation will give A plus 3B. B is 1 plus 2C is 4 equal to 8. So A equal to 1. So we got all the constants A, B and C. It's only a matter of putting it in the equation. Therefore, this equation becomes x of s is equal to a by s plus 1 the whole square. So 1 by s plus 1 the whole square right? Then plus, what is b? B is 1 by s plus 1 plus, what is c? It is 2 into 1 by s plus 2. Okay, so all these are in non-Laplace transform formats. Only matter for us is to find out the inverse transform. Okay, so what is the inverse transform of the first term? First term is 1 by s plus 1 the whole square, right? And you know t into u of t will be having a Laplace transform 1 by s square. That's the standard result. Okay, so what is the Laplace inverse transform of s plus 1 the whole square? S plus 1, you are converting s to s plus 1, no other change, s to s plus 1. So this is a frequency shift property, right? S is the convex frequency. You are shifting s by minus 1. Okay, s by plus 1. Okay, so what will be the corresponding change in time domain? It is e raised to minus t into tu of t. Okay, so a shift in the frequency domain will be corresponding to a multiplication by exponential signal, and s plus 1 means it is e raised to minus t here. Okay, that's the only difference. So the first term, inverse transform x of t equal to first term is t into e raised to minus t u of t. That's what we got here. Okay, plus the second term is 1 by s plus 1, and we all know its inverse transform is e raised to minus t u of t, plus third term is 2 into 1 by s plus 2. Again 1 by s plus 2, we all know its inverse transform is e raised to minus 2t u of t. So this is the inverse transform of x of s given in the question. Okay, the next question is to find the Fourier transform of unit step function, that is the Fourier transform of u of t. How will you find out the Fourier transform of u of t? Can we find the expression for Fourier transform? X of omega equal to integral minus infinity x of t e raised to minus j omega t dt. Can we apply that equation? Definitely no, because u of t is an infinite duration power signal. Such signals cannot be found out. They don't have an original f of t. They have only a limited Fourier transform. Okay, we have to apply some logical tricks and obtain a Fourier transform from some properties. We cannot directly apply the equation. Okay, I've already covered in some previous videos. Okay, so I have to apply some logics here to find the Fourier transform of unit step function. What I'm going to do is I'm writing u of t as u of t equal to 1 by 2 plus 1 by 2 signum of t. Okay, I'm writing u of t as half plus half scaled on signum of t. Is that right? Well, this expression half plus half signum of t gives you u of t. It gives, and I can prove it. Okay, be very attentive, I can prove it. Okay, if you can remember, this is signum of t. Signum of t is 1 for positive time intervals, write this, and minus 1 for negative time. Okay, and what is half plus half signum of t? Let me first do half into signum of t, then add half to it. Okay, what happens when 1 by 2 is multiplied with this signal signum of t? It is nothing but it's an amplitude operation. So all the amplitudes will be scaled by 1. So in the positive time interval, the amplitude reduces to half. From 1 it turns to half. Okay, what about a negative time interval? Again, minus 1 is multiplied by half means it is minus half. Okay, it will be reduced by minus half. Okay, so this must be a half signum of t. Okay, right. Now, so we have got half signum of t. Now what we do is we add half to it. You add half to it. Half is a constant at all time values. Never matter it is negative or positive time, for all time it is half. So I can draw it as I can represent half as okay, let this be half at all time intervals. Okay, right. So I'm adding this half with the half signum of t. Okay, this is half, okay. So what happens when you add this blue colored signal with this white colored signal? I can represent it in another color. Okay, what will happen at negative time interval? You will find half and minus half. What will you get if you add minus half and half? It will be 0, right? So at the negative time you will get 0 as the output signal. Okay, so now what will be the result at the positive time interval? This time interval, we have blue signal is half and white signal is also half. So half plus half is 1. So what you get in the positive time interval is 1. Okay, right. So this green signal, if you can see this, or I can draw it in another, I'm just redrawing it in another color for easily understanding. This red signal, okay, this red signal is the sum of half and half signum of t. And what is this red signal? What do you call this? It is nothing but u of t. Okay, so this red signal is nothing but u of t, unit step function. So whatever I have written as u of t equal to half plus half signum of t is correct. Okay, so if you have got a clear idea on this, let us move forward. Okay, so having understood how this equation is obtained, let us use this equation to find out the Fourier transform. Okay, before starting the steps, let me remind you two properties, two results. The Fourier transform of signal 1 is 2 pi del of omega. We have seen this in some previous videos. And the next thing is Fourier transform of signum of t is equal to 2 by j omega. Fourier transform of signum is 2 by j omega. How did you get this? We have already done this in elaborate method. I think in part 10 of this video lecture series, tutorial series, will give you that question, the answer to that question, or I will just use some hints to refresh your memory. This is signum of t, right? What we did was we approximated this as exponential signal, right? So signum of t was equal to 1 for t greater than 0 and minus 1 for t less than 0, right? We inserted e raised to minus a mod t, right, into 1 for t greater than 0 and minus 1 for t less than 0 into this equation. But in order not to change the mathematical value of this equation, we assume that limit a tends to 0. Okay, so if limit a tends to 0, e raised to 0 t is 1. So 1 into this thing is same as this equation. Okay, and then we proceeded by taking this equation, okay, for a transform of this equation, right? So then when we proceeded like this, we got the Fourier transform as signum of t as 2 by j omega. Okay, so I'm going to use these two results in solving this question. Okay, so what we have to do is we have to find Fourier transform of u of t, and that will be same as Fourier transform of 1 by 2 plus 1 by 2 into Fourier transform of signum of t. Okay, so that is equal to, what is Fourier transform of 1 by 2? You just have a look at this equation, this property. Fourier transform of 1 is 2 pi del of omega. So what is Fourier transform of 1 by 2? According to linearity, we can divide by 2 here also. So it will be pi del of omega. So the first answer is pi del of omega plus half into what is Fourier transform of signum of t? We already have it as 2 by j omega. Okay, so into 2 by j omega. So what is the final answer? That implies Fourier transform of unit step function is equal to pi del of omega plus 1 by j omega. Okay, so this is the Fourier transform of u of t. Okay, let's jump on to the next question. State and prove Parseval's theorem for Fourier series. Take care that this question is asked about Fourier series. Okay, not Fourier transform. So, any signal x of t, any continuous time signal, any continuous time periodic signal x of t can be represented in trigonometric Fourier series as x of t is equal to a0 plus sigma over n equal to 1 to infinity an cos n omega 0 t plus bn sin n omega 0 t. This is a trigonometric Fourier series representation of any continuous time periodic signal. Okay. Right. Next, what is the expression to find out power? Power, as you know, is given by 1 by time period integral over 1 time period. If x of t is a signal, then mod x square of t dt. This modulus is having importance when the signal is complex. So you need to take the magnitude only to square it. Okay. So this is the expression to find out power. So from this trigonometric Fourier series expression, what is power? Therefore, power is equal to, you find the integral of this signal square, okay, over 1 time period. So that becomes this RHS, we have to square x square of t means we have to square RHS, entire RHS. But entire RHS is the form a plus b. So a plus b the whole square is to be found out. Okay. So a plus b the whole square is a square plus b. I am treating the entire term as b. So this square means what is the power of this term? Here we have a cosine signal. Here we have a sine signal. We have already seen that the power of a signal like a cos omega ct is equal to a square by 2. Similarly, power of a signal b sine omega t plus 5. Here also plus 5, no problem. Okay, plus 5. Again, it is equal to, power is equal to b square by 2. You just need to consider the amplitude square divided by 2. Okay, so I can write it as sigma n equal to 1 to infinity the amplitude square by 2 plus again here also amplitude square by 2. Okay, so Parseval's theorem is an important, very useful theorem which relates the energy or power in time domain with that of the frequency domain. And what the theorem says is the energy or power is conserved in both the domain. Whatever, if you integrate and find out the power from this equation, using this equation in time domain, that same power you will get if you calculate this thing in the trigonometric Fourier series domain. Okay, so energy or power is conserved in a signal, whatever domain you are taking. Okay, so that is Parseval's theorem. So this is a slight proof of this Parseval's theorem in Fourier series. Again, if you're asked to find out prove the Parseval's theorem in an exponential Fourier series, you know, any signal, any continuous time periodic signal is represented in exponential Fourier series as x of t equal to sigma n equal to minus infinity to plus infinity cn, where cn is the exponential Fourier series coefficient. So cn into e raised to j n omega 0. Okay. So that is the exponential Fourier series. Now what is power? Power from this equation. Original equation is 1 by t integral x square mod x square of t dt. Okay, 1 by t integral modulus of x square of t dt. So what is the power from this expression? It is equal to 1 by t, or if it's for one time period, sigma n equal to minus infinity infinity. Okay, cn square into, this is cn, so cn square into e raised to j n omega 0 square, right? You would be thinking e raised to j n omega 0 square, but that is wrong, because I have already told you power is evaluated using mod x square of t. Okay, you take modulus wherever you find this modulus is having a relevance wherever you find a complex signal. Here e raised to j n omega 0 is a complex signal. So what is the magnitude of e raised to j n omega 0? E raised to j n omega 0 is actually 1 into e raised to j n omega 0. So the magnitude is 1. Okay, so cn square into 1, that is equal to sigma n equal to minus infinity infinity mod cn square is the power of power obtained from exponential Fourier series. Okay, again the Parseval's theorem says that power obtained from this equation in time domain will be same as this equation in frequency domain. Okay, so that concludes this question.